All right, so here's the situation. One of them we do know how to deal with. Excuse me. The other one we do not yet know how to deal with. It's talking about a baseball being dropped off a cliff and accelerating to the ground at a rate of 9.81 meters per second squared downward. And then at the same time, a cannonball is being launched horizontally with an initial horizontal speed of 20 meters per second, kind of similar to what we were doing in our marble rolling lab today, where things were being launched horizontally off a table. So let's deal with the baseball first, because that's something that we do know how to deal with. This baseball, since it's being dropped from rest, we can say that VO equals 0 meters per second for the baseball. And we know that it accelerates downward at a rate of negative 9.81 meter per second squared. That negative means it's going to accelerate downwards, so we're assuming up to be positive in this case. And it wants us to figure out the distance, the y distance that the baseball has traveled after the baseball has traveled for 1 second, 2 seconds, 3 seconds, 4 seconds, and 5 seconds. So I'm going to do one of them, and then I'll let you guys do the rest on your own. And the one that I'm going to do is I'm going to choose, just randomly pick 3 seconds. So we'll say that we know that the time equals 3 seconds. So we know that VO equals 0 meters per second. It accelerates at negative 9.81 meters per second squared. The time is 3 seconds, and we want to know how far that thing has gone vertically in that time period. So I'll quickly search through my equations, either from my textbook, online, or my notes are in my head. I have it memorized because I've done this before. This is the equation. This is the equation that we're going to go with. Y equals YO plus VOYT plus 1/2 AT squared. Now we know YO is going to be 0, even though we didn't really put that in our list of stuff, because we're just going to assume that that ball is starting from the origin. So we want to know how far it travels. So the distance YO is 0 meters plus an initial velocity in the y direction of 0 meters per second times 3 seconds. So that goes away. So does that. Plus 1/2. An acceleration of negative 9.81 meters per second squared times the time of 3 seconds. And I kind of ran out of room there, but that's okay. I will quickly do this calculation. 0.5 times 9.81. 9. I got that this had traveled a distance of 44 meters all around in that 3 seconds. So I can jot that down as being 44 meters after 3 seconds. And it's kind of on you guys to fill in the rest of these blanks for how far the baseball will have fallen each of those times. Now, the cannonball situation, that's kind of new. Whenever we're dealing with things being launched either at an angle or things being launched off of a cliff, I delineate between cliff problems and angle problems. For a cliff problem like this, I like to split things up into the x direction and in the y direction. Now, here's what I mean by that. This cannonball has an initial horizontal velocity of 20 meters per second in the x direction, but has an initial vertical velocity of 0 meters per second, just like our baseball had an initial vertical velocity of 0 meters per second. So we know in the x direction that this thing is traveling at a constant speed of 20 meters per second because there is no acceleration in the x direction. And we can make that claim that there's no acceleration in the x direction because gravity doesn't pull things side to side. It would be a little ridiculous if you were walking down the street and gravity pulled you to the side. Gravity only pulls you down towards the center of the Earth, between the attraction between you and the mass of the Earth. So we know while there's no acceleration in the x direction, there is an acceleration of 9.81 meters per second squared in the y direction, also downward or in the negative direction. Now we can use this information in order to fill out the chart for the x distance and the y distance of the cannonball. Now back to the baseball really quickly. We know that after 3 seconds, the baseball had traveled 44 meters vertically in the y direction. Now, if we look at our, let's also choose 3 seconds for the cannonball. So we'll go with 3 seconds for the cannonball to keep it similar to the baseball. So that means that after 3 seconds, the cannonball had gone 3 seconds in the y direction, has also gone 3 seconds in the x direction. So even though we're splitting stuff up into x or horizontal information, y vertical information, the times are the same in each the x and y direction. Time is what links things together in these problems. So now we could go through the motions and solve for the y distance at 3 seconds, or we could realize that this table of information right here is exactly the same as this table of information was when we were doing things for the baseball. So if we're going to try to find the same thing, use the same information, we can save ourselves the trouble and know that that cannonball traveled 44 meters vertically after 3 seconds. Now the x distance, or horizontally, we might have to do a calculation with this because we don't have anything set up so far, but this is a quick one. Since we know it travels with an average or constant speed of 20 meters per second, we can say, okay, it was going 20 meters per second for 3 seconds. So 20 meters per second for 3 seconds. Seconds is the same as seconds over 1, so cancel, cancel. That leaves us with a distance in the x direction of 60 meters. Now that means that the cannonball traveled 60 meters, 20, 40, 60 horizontally, while traveling 44 meters vertically. So we can fill in a point right there on this chart, and just like it's up to you guys to fill out this, 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 and this, once you find the y distances for the baseball, you also know the y distances for the cannonball, since the information is going to be the same in both. And you can also fill out the x information. That's going to be 0. We'll say that it starts at 0, 0. You can fill out the x information for the cannonball and then plot the points on this chart. So that's part 1, and you guys can do that. Let's see. So show your work for at least one row. This question, we'll answer this question tomorrow in class. We still need to finish up the lab and answer that question. So let's go on to the back. We'll do a sample problem very similar to that. In an effort to create a cannonball-style splash, 8-year-old Matthew runs off the edge of the board of the high dive at 4.6 meters per second and falls 2.3 meters to the water below. Determine the time for Matthew to fall the 2.3 meters to the water. There is a person. Is it going to delete? Nice. And this person is running at 4.6 meters per second while falling 2.3 meters to the water below. So there's the water. Water looks strangely like ground, but 2.3 meters to the water below. Determine the time for Matthew to fall the 2.3 meters to the water. Let's make this look a little flatter. Water will be flat. Okay, there we go. Now, we know when things fall that gravity pulls them downward. We know that the force of gravity causes them to go downward. And if you guys finish the first page, you guys will notice that the cannonball follows a curved parabolic path. We also know that gravity only pulls down. It doesn't pull side to side. So if my man Matthew is running at 4.6 meters per second at the start, then he is always going 4.6 meters per second horizontally as the time goes on, because gravity does not pull side to side, gravity pulls down, and if air resistance is off, which we're assuming it is, that 4.6 meters per second, there's no unbalanced force causing him to accelerate side to side, so he continues moving horizontally at 4.6 meters per second. But what would happen is he would pick up a little bit of speed vertically due to the force of gravity pulling him downward as time goes on. We know that he is in free fall, so that means there's an acceleration of 9.81 meters per second squared. All right, now our plan when we identify problems like this is we split stuff up into x information as well as y information, so vertical stuff and horizontal stuff. Vertically, we'll say that he always starts from, let's call this right here where he is, just draw our little coordinate system in. Say positive is up and to the right, and we'll say that he starts at the position X, O, Y, O. So in other words, he starts at the origin of our made-up coordinate system. We know that horizontally, he's moving at 4.6 meters per second, while vertically, he's moving at 0 meters per second because all of his initial velocity is directed side to side rather than up and down. We know that his acceleration side to side is 0 meters per second squared because gravity does not pull side to side, gravity only pulls downward, which means he has an acceleration of negative 9.81 meters per second squared. Negative because of the way we defined our coordinate system. If you want it to be positive, I don't really think it'll cause a huge issue with that because we don't have any initial velocity pointing in the opposite direction of the acceleration. Let's see, what else do we know? There's probably one other thing. Let's scan this information. We know that he falls 2.3 meters to the water below. That 2.3 meters, that's talking about his vertical motion. So we know that YO, his final position, is negative 2.3 meters. And again, if you wanted to do this to make your life easier, if you wanted to say that down was positive, I have absolutely no problem with that. That would make both acceleration and, I'm sorry, I miswrote this. My fault. That would make both acceleration and final position positive. I am just going to do it as being negative because that's the way I said I was going to do it at the start, and I don't feel like changing. But if you want to do it the other way, that's perfectly fine. We'll get the exact same answers. So at this point, the hard work here is done. We've set up our two tables. We've listed our information in the x direction. We've listed our information in the y direction. We want to find the time it takes Matthew to fall to 2.3 meters to the water. Now, if we had enough information, we could use our x stuff, or we could use our y stuff, because time is kind of what links these two problems together. The time in the x direction is equal to the time in the y direction, because the amount that you fall side to side in terms of time is how long it takes you to fall vertically. We have 4 pieces of information in the y direction, only 3 in the x direction, so I'm going to use the y information in order to solve for time. I will scan my equations list from either a former test or the quiz or somewhere online, my brain, and I will jot down this guy. Y equals YO plus VOYT plus 1/2 AYT squared. So at this point, it might be a little bit clearer why we were calling things X and Y earlier in a year, because things get a little confusing using both horizontal and vertical information at the same time. So I would go really slowly and make sure that I'm really listing everything in the X direction and Y direction so I don't make any mistakes. We know that our Y value, negative 2.3 meters. Our initial Y position is 0 meters. We have an initial Y velocity of 0 meters per second for blank number of seconds. 1/2. We know in the Y direction there's an acceleration of negative 9.81 or 9.8, depending on if you're doing a Regents problem or an AP problem, times t squared. We'll cancel some things that can cancel. 2.3 meters equals, that goes away. Negative, negative makes both of those positive. So 1/2, 9.81 meters per second squared times t squared. Do some math here with my calculator. 2.3 times 4.6 divided by 9.81. 3 times 4.6. 2.3 times 2 divided by 9.81 square roots. I got a time of 0.685 seconds. So a time of 0.685 seconds we got. Now, that's all this question was asking for, is it wanted us to find the time it takes him to fall to the edge of the water. And we can go back and we can add this to our list of information. We can say that the time is 0.685 seconds horizontally, as well as being 0.685 seconds vertically, because the amount of horizontal time that you're in the air is the same as the amount of vertical time you're in the air. Time is what links the X and Y stuff together. Now, the question didn't ask for it, but let's say the question asked for something along the lines of how far away in the X direction did this person land from the base of the diving board? Well, now you can use your X information because you have 1, 2, 3, 4 pieces of information there. You can apply one of your equations. He's moving with constant speed, so you can say that constant speed equals distance over time. His constant horizontal speed, the X direction. So sometimes I do this just to let myself know I'm talking about X stuff. 4.6 meters per second equals whatever distance he travels in the X direction over a time of 0.685 seconds. 4.6. The distance that he travels horizontally is 3.15 meters. Which is a pretty impressive dive. Go. This sample problem links up with page 56 and 57, kind of before that too. 54 and 55 we'll go over in class tomorrow. But this is really page 56 and 57, which is a sample problem about horizontal projectile launch. I would make sure that you know how to do that, because tomorrow in class we will do a lab where you need to predict how far something will go when it is launched horizontally. So finish up the first page of this packet, maybe take a look at the textbook, and make sure that you are good with the sample problem that we just did. I will see you guys tomorrow in class.